Hi, in this fourth video for Waveform Generator we are going to look at the value converters. We begin here with a close-up from the manual to show that diagram I have shown a few times in the previous videos. When generating advanced waveforms, we begin with a phase. That phase is put through three phase converters that might change the phase. Then that phase is passed on to the basic waveform algorithm, and it will calculate a value in the range from -1 to +1, and then that value passes through three value converters, and each value converter will take this input in the range from -1 to +1 and change it to another value also in the same range from -1 to +1. So let's see how it appears in the software. We begin by adding an advanced waveform, and I simply choose a sine. And in this video I will only concentrate on these three value converters. The first one, linear, it will simply pass the input value out as an output value without changing it. So right now these three value converters are doing nothing. If we choose the first one, inverter, it will simply multiply all input values by -1. So the value of 0 remain being 0. This one was up here before. +1 multiplied by -1 becomes -1. This one should have been -1, but multiplied by -1 it becomes +1. So we have in effect inverted this waveform. In some cases, the phase converter inverter or the value converter inverter will produce the same output as is this example here. Here we have inverted the values. If we go back and invert the phase, we will see the exact same result. However, it's not always the case. This inverter up here will invert the waveform across this line here at 180 degrees. Whereas this one will instead invert around the 0 line. So depending on the waveform you might get different results. The next value converter is called a half inverter, and what it will do is it will invert the top around an imaginary line here at 0.5, and it will invert the bottom around the imaginary line at -0.5. So we get this result instead. Like the inverter up here, you can choose a range, and likewise with this one also. It defaults to invert the entire waveform from 0 degrees to 360 degrees. So we could choose we'd only invert the first half of the waveform by choosing from 0 to 180 degrees. Next we have this one called force sine, and it will force the sign of the values to either be positive or negative. Here we have the 0 line. All values up here are positive, and all values down here is negative. And right now we force all of the values to be positive. So this part that would normally be down here is now forced to be up here. We can also choose all values to be negative, or we can choose that the first 180 degrees of values are positive and the last 180 degrees are negative, or vice versa. I use this one from time to time to turn a waveform into only positive values, because it makes it more easy when you are multiplying waveforms. You don't have to do it, but it's one use of this. And also you can produce different waveforms. For example, if we choose the random linear, we can, for example, choose the first part should be positive and the last part should be negative by using the force sign. So we get this result instead. Next in line we have the volume. It defaults to 100%, meaning it will not change anything. But you can reduce the volume and you can increase the volume. At some point you will see this star up here, and this star indicate we have a soft clipping condition. It's simply the program is telling you you are not seeing the entire waveform. You have something either above +1 or below -1. If that is the case, you can choose to add a volume value converter, and you can simply use it to lower the volume. You don't have to do it because on export the waveform will automatically be normalized. But in most cases I will tend to do it because I like to see the full waveform. Choosing to lower the volume, if you don't do it, I know in this case it's just a sign, so I know what happens outside what is displayed. But it could be you could have combined two waveforms, so this did not have to be a perfect arc up here. It could be everything else, and by lowering the volume you can see what it is. And also you can do operations that will lower the volume. For example, if I add this, if I change it to a triangle and I add a smoothing, you see here this operation have lowered the volume. So I could choose to add a volume value converter to increase the volume. But again, it's up to you. You don't have to. Next, we have this hard clip. And it works a bit in the same way as it can increase the volume. It defaults to this auto gain. I will disable that. Now you can see introducing the hard clip with a settings of 90% means that everything that's above 90% or below -90% is simply cut. So we introduce this hard clip, and normally it will default to this auto gain. And when auto gain is enabled, it will automatically increase the volume. And now we don't see the soft clip warning because there is nothing above it have been clipped here. So instead of lowering the volume, if you have a condition with a soft clipping, you could choose to add a hard clip, but you need to be aware that it will include this clip in the file, and it will change the waveform, how it sounds. Next, we have this one called peak wrapper. And what it will do is it will also increase the volume, but instead of either clipping or letting the waveform go outside the bounds, it will wrap it around. So this peak that should have been up here has now wrapped its direction, so it's going downwards. Likewise, this one has been wrapped also, so it will start to grow upwards. So as we increase the volume, it will go until it hits the bounds again, and then it will wrap again in the other direction, and so forth. But you have a variation here. You can choose the wrap point. It will always wrap up here and down here, but you can choose that instead of it should keep growing downwards until it goes down here, you can see it say that it should wrap again when it hits the 0 line. So now when I increase the volume, it will hit the 0 line, then it will wrap again, and then will be repeating its operation up here. And you can move that point further away from the 0 line. For example, I can choose 0.25 0.25. So as I increase, it will wrap at this point, and you can move that up. So you can use this to generate different waveforms. And it's no matter which waveform you input. For example, it's to choose a sync. You can get these strange waveforms. I wouldn't normally think, looking at this, that it would be a sync waveform that produced it. Let's go back to assign. Next in line, we have this shift reducer. And this value converter is doing two things. It will shift the waveform either up or down, and it will also reduce the amplitude of the waveform. So here the entire waveform have been reduced to only occupy the top 25%. You can go all the way to only 1%. You can continue down to full 100%, and then it will start to go to the bottom instead. I will often use this shift reducer when I'm multiplying waveforms. For example, if we go in here in compound waveform and we choose a sine, and we can choose sine again, or let's choose a triangle, and we can add a shift reducer and say it's okay like that, and then simply multiply them, and we get this result. So that's one usage of this shift reducer. Next, we have this DC offset. If for any reason you have a waveform that's not in the center, or you don't want it in the center, you can push it either down or up. So what we did before with the shift reducer, you can do manually. For example, we can add a volume, reduce it, and then shift it to the top. But in this case, I would use the shift reducer because it's more easy. Let's add a smoothing again. And do heavy smoothing. As a result of heavy smoothing, you can see this part is now a little below the zero line, and also in this end. So one way to fix that could be using the DC offset and simply move it back up. Next, we have this one, set 0. It will not be a value converter you would use very often. It lets you set a specific range of your waveform to be 0. In the manual, I have a description of the cases you might want to do that. But if you need to set parts of the waveform to be 0, you can do so by setting these two values. Next, we have the fade in, fade out. Again, let's do this heavy smoothing. Before, we used the DC offset to push the entire waveform upwards. Another thing you can do if you find that these are not at the zero crossing and you want to force them to the zero crossing, not that you have to, but if you want to, you can choose to use this fade in, fade out. It will operate in the beginning of the waveform and in the end of the waveform. And you dial in a range defined in degrees, saying how long time should it be to fade in or fade out. So you can see as I increase this value, I get this effect. Now I have forced my waveform to be here at the zero crossing, or the zero line. And then you have different kinds of fades. And instead of memorizing how they work, normally I will just move my mouse over here and use the scroll wheel, and I will go through them and pick the one I find that I like the best. In this case, I would probably choose this one. So you can do your fades like this if you need to. For the next, let's dial in a different waveform. I want to do a square. For example, with 56 harmonics. At this point, there's no problem for these. It's the same waveform. It gradually goes from the top part to the lower part without any issues. But in the program, you can combine different waveforms. So this point where they meet can be not so nice looking. So what you can do is you can do this pi fade in out. As you probably remember, the phase of the entire waveform is 2 pi. So pi is here at 180 degrees, and this is here where this one operates. And like before, you simply choose the range it should perform this fade. So you could set it up like this. And then you again have different ways of performing this fade. And then again, I would go through them and pick the one I like the best. In this case, I like this one. So that would be the one I would pick in this case. And you can make it extreme also. So that's the pi fade in out. Next, we have the smoothing. I already shown it, but let's have a look anyway. Let's do... I'll just remove this one. Here we have some sharp peaks, and if we add a smoothing operator, we can dial in a range it should smooth. And the smooth value converter can be a bit heavy on the CPU, because what it will do is, for example, this peak up here, it will now read some values 10 degrees, 5 degrees to each side. And in that range, it will take 13 samples, and then the value it would use would be an average of all those samples. And the more samples you dial in, the more times it would have to call this waveform. For example, let's assume this illustration is 1000 pixels wide. It means normally we would call this function 1000 times. But now for each of these values, it have to read 47 values. So instead of calling this method 1000 times, it will call it 47,000 times. And you can also have multiple smooth operations. And now you really get starting to put a workload on your CPU. If you have used the smoothing operator, the value converter, what you can choose to do is you can choose to resample your waveform into a hand-drawn. And when you do that, the effect of the smoothing, the smooth value converters will be applied to that hand-drawn waveform. So they are no longer inactive because their effect is already included in the waveform. Next, we have the sample and hold. We already looked at the phase converter sample and hold. However, the value sample and hold converter will have a similar output, but still it will be different. Instead of having a fixed phase, we have fixed sizes of the step. So you see this part is more narrow than this part. However, this step have the same size as this step. So it's two different ways they work, but they produce similar output. Next, we have this start and end sample and hold. And I don't think it will be a value converter you will use very often. But sometimes I have used it, and it works a bit backward. You can choose have it to work in only here at 0 degrees, or only at the end at 360 degrees, or like a default here at both ends. And here set to 30 degrees, it will call into the waveform and ask what is the sine of 30 degrees, and then that would be the value it will hold for the first 30 degrees, and likewise in this example here also the last 35 degrees. Choosing a triangle, we get the same result. However, if you choose a square, you don't see a change because that value is held for the first and last 180 degrees. So how it works will depend on your waveform. Next, we have this sample reducer. And the way it works is it will take this number of samples from the waveform and then throw away the rest of the information. Here we have taken 5 samples, 1, 2, 3, 4, 5, and then it will just make linear interpolation between those 5 points. The rest of the waveform we don't care about. And by choosing different number of samples, you get different results. And as you can see, you have a combo box here. Instead of linear, we can also choose to draw S-curves between the points. And depending on the waveform, you'll get different results. But as you start to get more samples, you get this rippling effect. Next, we have this for adding a random noise. And it will simply add a random noise to your waveform. And you can dial in the amplitude of this noise. And while it adds this noise, it will always automatically reduce the amplitude of the waveform so you don't get into a soft clipping condition. You don't have to add a value converter afterwards. So you can see here. Another feature with this random noise is you can also set the width of each noise grain. Here we have a very thin noise grain. We'll have one noise grain per 4096 samples taken from this waveform. But we can start to dial in a bigger number and we get this effect instead. So you can choose many different waveforms simply by adding this noise. Next we have this ripple effect. And it would add ripples that have a sinus effect. Here we can dial in the amplitude of these. And we can dial in the number of these ripples. So simply scrolling the mouse wheel, you can have this effect. Next, we have this analogish. What it will do is it will add it like the phase converter that worked in the x-axis. This one is working in the y-axis, so it will affect the amplitude of our waveform. And like the phase converter, you will have multiple steps, either 2, 3, or 4 steps. And for each of these, you will have 100 seed values to randomize it. So as I'm going through these different values, you can see the waveform will be pushed up and down at different places. And I like to combine it with this one. So for example, save out this waveform, change both of them, save it out again, change both of them, save it out again, and so on. And you can produce a waveform that is not static. It has a little change. And you can make this change extreme by dialing in a large number, or you can reduce it to only have a little effect. Here you almost don't see it move. So it can make an otherwise digital waveform sound a little more analog. Next we have this expand contract. We also had one up here. And while they're both implemented in different ways, they have more or less the same effect. Here we have split the top part into 2 bands and the lower part into 2 bands. And that part we are both expanding and contracting. And that will introduce this ripple effect. So as we increase it, we'll have small ripples here. They're hard to see. You can see it's not a perfect smooth sine. But as you increase it, these ripples will be fewer and larger. Next, we have this exponential. We had an exponential up here also for the phase converters. Here we have an exponential working in the y-axis. And here we see the sign. We can almost change it into a square. Here it looks more like an ellipsoid. And we don't get a perfect triangle, but we can start to change it into this. And of course it depends on the waveform you have, how it will appear. Next we have this mid shift, and it's very hard to describe what it's actually doing. I suggest you play around with it and read. I have tried to describe it in the manual, but you can produce some interesting waveforms. We can do like this with the sine or with the triangle, or with the sync. So play around with it and see how it works, and read about it in the manual. Next we have this half pi mirror-invert. And it's also one of those that can be a bit difficult to get your head around. Let's dial in a sign like this. What it does is it will only use this part of the waveform, these first 25%, and then it will throw out the rest. These first 25%, it will mirror across this line. So in this case, this shape we have here, it will be mirrored to be over here instead. When it have done that, it will take all of this part up here and mirror it downwards to this part. So in this case, where did it go? Here. So in this case, we get this shape. it's only this part we're using. The rest is simply mirrored and flipped versions of this part. And depending on which waveform you use, you'll get different results. For example, using a sine, you will not see any change at all, because this part is already a mirrored version of this part, and likewise this one is a mirrored and flipped version of this part. Choosing, for example, the random linear, we will get different results. So that's the half pi. We also have one called pi Mirror-Invert. And what that will do is it will take a copy of the first 180 degrees, flip it and invert it to the rest. So instead we get this result. Or if we choose a rounded version. Next we have this half pi Interpolate. It will also be one of those value converters you'll probably not use that often. Let's try to dial in something. It will work around half pi, meaning here at 90 degrees, and it will work here at 180 degrees. And what it will do is it will push 2 points outwards to the left and right, and then it will linear interpolate between those two. So right now, from this point to this point, it throw away the data that's in the waveform, and likewise from here to this point, between these 2 points, it will also throw away the actual waveform. And then in this case linear, it will simply add a straight line between those 2 points, and you can set it up to do an S-curve instead. So you can get these results like this. In some cases you might want to use them because you have something strange going on the way the 2 parts are connected. If you cannot exactly get the effect you want, you can simply choose to resample your waveform into a hand-drawn. Once it's resampled, you can do whatever, for example, drawing an S-curve between those 2 points. But of course, if you can get the result you want, there's no need to go in and hand draw it. Next, we have this one called Pi-Invert. It works exactly like the other one we had before, but instead it will work only here at 180 degrees. So as I increase this value, it will change, again, throw away the real waveform and do a straight linear interpolation or do an S-curve interpolation. This one you will probably use a little more than the other one, because you can have waveforms where the left and the right are not meeting like you want. For example, you can also, like we saw before with, let's remove it for a second. Here we can choose to add it to interpolate between these 2 waveforms, and you can get this effect instead. So it works different than the fade we looked at before, previously. So you can, this is not a fade, it's simply an S-curve that's being drawn. Lastly, we have this one, free interpolate. It's only linear interpolation, but you are free to choose from where to where. Sorry, it was not this one. We can say I want to interpolate from 45 degrees to 190 degrees. And it's simply always a linear interpolation, but you can choose. If you want a different result, instead of using this one, simply resample into a hand-drawn, and you're free to do whatever you want. For example, if you want an ellipsoid to connect these parts, you can do it simply hand drawing it. But in the cases you can achieve what you want with these effects, I would choose to do it, and only if I'm not able to, I would choose to resample it into a hand drawn. So these are all of the value converters, like the basic waveform, the phase converters, and so on. All of these are mentioned in the manual. If we go here and open the manual, and here we scroll to the table of contents, you have description of all the waveforms, all of the phase converters, all of the value converters. And in the last chapter, I will go through the advanced waveforms, the partial waveforms, the compound waveforms, and regarding the compound waveforms, I will mention all of the operators you can use.